Assalamu alaikum wa rahmatullah. Hello everybody and welcome back to our tutorial Mastering Autodesk Inventor from zero to hero. In this video we'll discuss a subject that's related to mechanical engineering design and mechanical engineering drawing, limits, fits, and tolerances. What's this and why do we need it in our design and how to do it in our drawing? We know that every manufacturing process is a combination of three elements: man, machine, and material. These three elements affect the accuracy of production. Okay? And due to unavoidable inaccuracy of manufacturing process, any part cannot be made precisely to its given dimension. Which means we have here, this is our aim part with dimension of L nominal, could be 50, 100, etc. mm. Okay, for example, a length of this part. We gave material to people to work on machines to produce this part. The result is here. The result. Then we have 21 parts here that are produced. Okay, with people on several machines. Okay, let us say the same material. As we can see here, they are vary from the nominal dimension, from the nominal length. Some of them are bigger, some of them are smaller. Depending on our device that our part will be fitted in our condition of work for this part, we have limits, what we call limits. And we have L max, maximum size allowed, and minimum size allowed. Any part will be above the L max, a waste. And any part will be lower than L minimum, it's a waste too. In this here we have two parts bigger than the max allowed dimension, and we have two parts smaller than the minimum allowable dimension. These parts are waste. The other parts are, we can use them in our production. And then in this case, we go to a fact that there is no such a thing as an exact size. When we talk length of 50, in real life it's not 50. Exact 50. It's plus, minus. Let's go further. Important terms in single part definition. The nominal size Ln that we talked about is general size usually expressed in amps. This is the size that we nominated for this part. Limits. The extreme permissible values of dimension. Maximum upper limit and minimum lower limit size shown by tolerances. What's the tolerance? The tolerance, the total amount that a specific dimension is permitted to vary. We are permitted to vary from to. Okay? The difference between the maximum and minimum limits for dimension. Then these three terms we have to understand. standard tolerance grades. The grade of tolerance, it's an indication of the level of accuracy. We are talking about accuracy. And we have 20 standard level or grade of accuracy from IT01 to IT18. And here examples, okay, about manufacturing or production, what products are in these levels. For example, from IT01 to IT4, it's for production of gauges, plug gauges, measuring instruments. IT5 to IT7 for fits and precision engineering application. IT8 to 11 for general engineering, which is our work, will be most of our work, our design will be here in this range, from IT8 to IT11. IT12 to IT14 for sheet metal working, press working, okay, and IT15 to 18 for processes like casting, general cutting work, okay, where we don't, we are not interested that much in accuracy. Here the table, values of standard tolerance grades for nominal size up to 3 to 100 mm. And here we have our grades, 01, K0, 1, 2, 3, etc. And here we have the dimension. Let us take an example. For example, if we took a 30 mm dimension, here's the 30 mm dimension. Here we have above and up to. Okay, then from 30 to 50, here from 50, sorry, from 18 to 30, and here from 30 to 50, then we'll take this row. And here you can see that when we are in the high accurate level, 01, we have 0.06 micrometer to play with. The tolerance is 0.6 millimeter, micrometer. When you go further from this 30, okay, until let us take IT7, and then we have here 21 micron. Okay, our tolerance is 21 micron, 21 micron. Then we talked about 21 micron to play with, up, down. Then the difference between maximum and or upper or minus lower limit is 21 micron. Okay, when we have 30 mm, okay, with 7 level, also IT7 grade of standard. Here, some manufacturing process, I put a table, manufacturing process and the IT grades will be useful, okay, for you when you are designing your projects. Let's talk about characteristics of tolerance and their possible position on the tolerance zone. Then we have actual size L, nominal, okay. The actual size is a measured size of the finished part. Actual size, we have Ln, it's nominal size. We are screening for, okay, our goal is to have a 50 mm part. This is nominal size. Actual size, when we measure our part after production, okay, that could vary between L max and L minimum that are allowed according to the grade that we selected. Okay, and here L max, maximum size of our part or maximum dimension, will be nominal plus upper deviation, and the minimum size or minimum dimension will be nominal minus lower deviation. In the case of our tolerance zone is on the zero line. Zero line is the nominal dimension. Okay, and here is the and here we have upper tolerance above the zero line. Lower tolerance is lower deviation. Upper deviation, okay, above the zero line. Lower deviation is below the zero line. Upper deviation minus lower deviation will give us our tolerance. This is our tolerance. We talk about 30 mm at IP7. Even this dimension be 30 or 21 micron. Some of them will be above, some of them will be down, for example. So, next position, when our tolerance is above, this is my zero line, okay, and the tolerance is above the zero line. In this case, as we can see, this is our nominal length or nominal dimension, okay? Then both the maximum, the L max or L min will be plus the upper deviation plus the lower deviation. L max will be all the time bigger than L nominal. Next case, when our tolerance is lower or under the zero. In this case, L max and L minimum will be less than the LN, less than the L max, then minus upper deviation, L minimum minus lower. And these three possible variation of tolerance position, possible position of tolerance zone. In standard, we have here possible positions of the tolerance zone in the case of holes. From standard, ISO standard uses tolerance position letters with capital letters for the hole. When we saw capital letter, which means it's a hole tolerance, and beginning from A until Z, here and ZA, ZB, ZC. The same way, here we have table isotolerance for holes. Okay, here we have dimension from 3 to 6. Okay, on over 3 and include, etc. until 400 mm. And here we have the most used tolerances for holes. 6, 7, 11. We said from 7 until 11, from 6 sometimes. Okay, this is our mechanical work. Here is a table from where we can find according to dimension, okay, and the level that you want to work with, level of accuracy, find the tolerance, upper and lower deviation of that tolerance. The same is for the shaft, but here, as a standard, uses tolerance position letters with small letters for shaft. Sorry, there's some mistake in here for shaft or it's for holes. Okay, then for shafts, we use small letters. The same starting from A until BC, and this is my zero line here. Okay, and this is the possible positions of tolerance. Okay, on the zero line, lower or above. And this is the table, the same table as for holes, but here for shaft, and you can see here small letters. You can see here small letters, and numbers is the grade of accuracy or IT, the national tolerance grade. Fit between mating parts, fits between mating parts. This is the end aim or end way that will end it to make parts together, to assemble these parts together. That's why we have to give them a tolerance. Okay? We assemble parts together. We need our device to work under certain conditions that we put in our design. Here we have three types of FETs: clearance FET, interference FET, and transition. Clearance FET. Tolerance of mating parts always leaves a space. And we have clearance all the time. All the time we have a space between two mating parts. Interference FET. Tolerance of mating parts always result in interference. They are interfered in all times. Transition FET sometimes interferes, sometimes clears. Okay? Then sometimes we have in some of assemblies we have interference, and some of them we have clearance. Let us see. Clearance FET. For example, here for 550 H7, okay, we took for the hole, and 550 F6, we took for the shaft. And the mating parts have such upper and lower limits that the clearance always results when the mating parts are assembled. But the bigger shaft, we have two sizes, L max and L minimum for shaft, and we have two sizes, L max and L minimum for hole. Yes. And the bigger shaft is smaller than the smaller hole all the time. Just see, and it leaves, that always leaves clearance. Can you see? And we have a clearance here. Next, transition FET. Either clearance or interference may result depending on the exact value of dimension. As we said, we could have clearance, we could have interference. Okay, both cases are here, can happen. And this is my case of transition FET. Some of holes will be bigger than the shaft, some of them will be smaller than the shaft. Okay, transition FET here, as we said, interference FET. The mating parts have such limit that the lowest shaft diameter is larger than the largest hole diameter all the time. Okay. The small shaft always bigger than the big hole. So we have all the time we have interference. Let's see. Can you see? And we have interference. We have an interference here. My shaft is bigger than my hole. And these three types of FETs that could happen in our assembly depending on our design. Here I put tables, preferred FETs and tolerances chart. Okay. The preferred metric FETs and tolerances for hole and shaft based system, which are given in ISO 2861, 2010, and NCB 4.2 at 1978 here. Standards are summarized in the following tables. The usage of the tolerance is advised to economic reasons. And here some suggestions. Okay, we have type of FET: loose FET, free running, easy running, sliding FET, okay, close clearance, patient clearance, and all these are clearance FETs. Here we have interference FET, press FET, medium FET, force FET. Here we have transition, slight interference, etc. We are designing, we can choose from here, okay, what case your design or your device will work under, what condition. Here, another table, it's almost the same, and shows clearance FETs, okay, for hole and hole basis and shaft basis system. And here description. Here description, for example, if we take H8, F7, here we have close running for running on accurate machines, for accurate locations of modulation speeds and journal pressure. These are information for you when you are starting design your senior or junior project. Next, how to read part dimension with color. And in case of hole, then we have here 536 M6, for example. 536 is the nominal diameter, and it is the tolerance zone. We have from A to G. And 6 is IT grade level. 6 is IT grade level. We read it 536 M6. Okay. Here we have two sides that we have to understand according to this note. With adding dimension with tolerance to parts, you must show tolerance value or limits sizes and 3-digit precision. Then when we are putting a dimension or adding a dimension to a part, we have to show it this way or this way. 536 M6, it's not enough for a part detailed drawing. Because anybody who will produce or working on production for this part, you will not go to tables and find how much the M6, etc., etc. You have to put these sizes maximum, okay, and minimum size for the part or tolerance. Okay, you have to show them in your drawing. What about shafts? As we said, holes have capital letters, but shaft has small letters. Here, 546, 6, for example. Okay, here is the tolerance zone letter with a small letter. 6 is the grade level and nominal dimension as in shafts. The same way for shafts, adding dimension with tolerance to part, you must show tolerance values or limit sizes, 3-digit precision, as we see here, 546 P6, and the maximum size will be 46, 0.42, or the minimum size will be 46, 0.26, or we have here 46, and we are giving the tolerance, so the tolerance. How to read assembly dimension. When we are coming to assembly, we have two making parts share the same diameter. For example, 46, we have two parts that share these 46. And here at the top, we have N6 for the hole, and we have P6 for the shaft. You see, tolerance, hole tolerance, is tolerance zone and level of accuracy. Here P6 for the shaft, and we have hole and shaft. Okay, inside dimension, outside dimension. We can write it this way. Okay, and we can write it this way with a slash. The same. 546 N6 slash P6. Okay, and this is how on assembly our tolerance or our pet here will be shown. Example of assembly dimension with tolerance. And here, real example from our drawing. As we can see, at the diameter of 50, we have H7, F7, H8, F7. Okay, with the shaft and the head. Here with bushings and shaft, we have 536 H7 G6. It's a clearance. It's a reference fit here. I don't want my bush to move inside the base. Okay, then 546H7 P6 interference, and my shaft have to rotate slightly, a little bit clearance have to be between shaft and pushing. That why we gave 36H7 P6 here with shaft and bushing. And this way we show our fit for an assembly. What about parts? And here example of parts dimension with tolerance. In parts, as I told you, we have to show, okay, the size, or we can show the tolerance. And here we have Python 6H7, 36, the upper side or maximum size is minimum size. And here for the shaft, we outer, we have inner dimension here, outer dimension. We'll call it as a shaft here, okay? Then 546P6 exercises. The same here for the whole 46 that my pushing will be in. As I told you here, it will have the press fit. Next, ISO system of limits and fits. Okay, for your information, the ISO system of limits and fits, referred to as the ISO system, is covered in national standards throughout the world, as shown by the following list. In here we have global ISO 286. In USA we have NC B42, B42, B4.6. In Japan, GIS B0401. In Germany, France, UK, US, Italy, etc., etc. I hope you understand and enjoy. See you in next video. Thank you for watching. Keep tuned.